Okay, we're on page 312, or 314 rather, talking about statistical sampling. And the idea is, instead of having to test everything, I do a random sampling of this, and based upon the random sampling, I can kind of infer the rate of errors that I'm going to find in the lot. So whatever the lot is versus the sample size. And the idea is, I don't have the time and energy to test every single one of them, so I don't. So the question really is, how do I determine the sample size? Well, there's some math involved, doggone it. And so one of the math is, what is the certainty? What is your desired certainty? In other words, and here's how the way you ask that question. Do you want to be 95% sure that your sample, let me start over. You want to be 95% sure that your sampling is going to be representative? That if your sample passes, you're okay, and if your sample fails, then the whole lot fails? How certain do you want to be? And so mathematicians have come out and said, and here's the factor we're going to use, and don't worry about how they came up with it. This is not a math course. But so you pick the desired certainty, and you come up with a factor. So in the book on page 315, they talk about the way you determine the sample size is you take the uncertainty factor divided by the acceptable error, and then you square it. Okay, so I know, don't let your eyes glaze over just yet. All right, here we go. So let's say that I'm 95% certain that I can catch the error with a sample. All right, that means my certainty factor is 1.96. And then I have an acceptable error rate of 10%. In other words, if it's more than 10%, okay, I got to do something. If it's less than 10%, I'm going to let it go. All right, so 95% certainty and 10% acceptable. So that would be 1.96 divided by 10%, which would be 0.1. Okay, that would be 19.6. Okay, and then you square 19.6, and you end up with 384. So in order to be 95% certain that I'm going to catch my errors at a 10% acceptable error rate, I need to look at 384 items. That's how you calculate your sample size. Okay. The next thing you talk about on page 315 is Six Sigma. Now, in math world, Six Sigma abbreviates a Greek letter, but they typically use it when they're talking about standard deviation. And if you've never taken a math course, just nod your head and go, uh-huh. I'll show you a picture of this in just a minute. But so Six Sigma basically means 6 standard deviations out. The technical definition of Six Sigma is like 3.4 defects per billion. That's with a B. No, it didn't. Million with a B. Let me start over. 3.4 defects per million, not with a B. I'm sorry. Okay. That's the technical definition. But that's not what they're talking about here. Six Sigma here is the name of a quality control philosophy that basically goes back to this guy over here and says, we're going to use charts like this, and we're going to, instead of just allowing the upper limit to be 12.1 and the lower limit to be 11.9, as we get better and better and making it kind of go, float in the middle there at the 12 level, we're going to start making it more difficult. We're going to start changing the upper limit and the lower limit. We're going to start pulling it in. So that's what Six Sigma is all about, is as you get better, you do better. And as you get better at that, you do better at that. And you just keep going and going and going. So you start off with an upper spec limit and a lower spec limit. But you may not end up with that, because Six Sigma might draw it in and make it a little bit more, make it a little tighter. Okay. So the whole point of Six Sigma is reducing variations. So there's this thing called a DMAIC. That's just an acronym. It basically stands for define, measure, analyze. Okay, so let me just start with the D, the define. So defining the problem or opportunity, I'll admit, you could use Six Sigma for coming up with new things, but most of the time we're talking about defining the problem. So D is define, and then M is for measure. I have to go out and measure, collect data like this, okay? Then I have to analyze it. So yeah, like the whole point of the 7-run rule and those kinds of things. And then I have to improve it. I have to take some actions to improve the system and improve my quality control measures themselves. So as I become better, I shrink the limits in. So after doing this thing for several months, my specs might be, instead of being plus or minus 0.1, it might be plus or minus 0.05. And so I've taken this chart and squashed in half. And then C is the control. And the control basically is prove it. It's all about, make sure you're within the specifications of your, now if you've tightened them up, are you still there? And then you just continue. This thing never stops. Okay? Six Sigma isn't about, we ran a Six Sigma, so we're done. No. You continuously keep going and keep going and keep going and keep going until you've kinked out all of the things and you've got it as tight as it can go. As tight as specifications as you can possibly make it. That's the idea behind Six Sigma. Okay, so there's some principles there, so let's talk about the principles. Well, to tell you the truth, this is an organization-wide commitment. It's a culture change, okay? And this is kind of the key to this. If the whole organization hasn't bought into this idea of just continuously making things better for the sake of making things better, in other words, the manufacturer might say, look, there's nothing wrong with plus or minus 0.1. There's nothing wrong with that. But no, I want to make it 0.05. Okay? So you see what I'm saying? This has to be a kind of a cultural thing. No, we got to do the best we can every single time. And the training, they use like martial arts things. They have, a green belt and a black belt and all these, these goofy things. I went to black belt training. I never actually finished, by the way, but I went to black belt training on this and became a Six Sigma black belt. Is somebody who's spent several weeks of training on basically how to do this, and a lot of it is not mechanical. Okay, when you go to this training, it's not that much math and statistics. It's more about philosophy and how to convince people. So they talk about how in this world it's easy to kind of get lost in the forest because of the trees. In other words, you have to be able to have both focus. The big picture and what's the size of that whole. The creative and the rational. The big picture and the details. The quality and the cost. And the customer satisfaction. All these multiple things, all part of it. And so, if you buy into this thing of Six Sigma, it's basically an entire operating philosophy that happens everywhere in the entire organization. I mean, not just the software IT project we're working on. We're talking about, recruitment at the HR people and finance and accounting with payroll. Everybody absorbs this philosophy to make, hiring and firing better, to make payroll operations better, plus making your software better. It's a corporate-wide thing. And I can tell you there are people that buy into this, and there are zealots out there that are almost as crazy as the agile zealots. I mean, yeah, you can drink the Kool-Aid here, okay, and really get into this. Okay, so continuing, let me get to the right page, 318 here. We're talking about the statistics of it. So here is what's called the normal distribution. So the premise behind this is, if you were to take things that are random, okay, just things that are random, and start determining, there's going to be an average. So I don't know, let's say this is grades on a quiz. Now those aren't necessarily random, but let's just assume that they are. The grades on a quiz. And the average grade on a quiz was a 72. Well, you could say that the one standard deviation is that first 68%. So 68% fall within that range. And then the next standard deviation is 95% fall within that range. So that basically means if your score on this quiz was outside of 95%, in other words, you're at 4.5% of the total, that means you are definitely an outlier, aren't you? Okay? So this is a way of grouping things in standard deviations, and I'm not going to bore you with the math. So that's what the standard deviation is all about. So they go ahead and say, well, if plus or minus 6 sigma is what percent of a population, and then this defect units per billion. And again, I'm gonna let your eyes glaze over on that one. That's okay. And then the next one they talk about is how do you normalize this for what's called defects per opportunity, defects per million opportunity, and this is where that 3.4 came out. So basically, 6 sigma means the data you're collecting is 99.99966%. Wow. So is 6 sigma really appropriate for everyone? No. I mean, yeah, you probably could spend the money to try to get that tight of a grouping, but to tell you the truth, that's probably not cost effective everywhere. Okay, you only want to use that. You only want to squash that thing down so tight on things that matter. Okay, not things that don't matter. Okay, I'm going to move on from the math and go to page 320, talking about testing. So there's all different kinds of testing, and one of the kinds of testing does not occur in the testing phase. Okay, so remember we talked about how initiating the project, and then when you have planning, and then you have this, the design thing and the development part, and then you have a testing phase, an implementation phase. Okay, well, during the development phase is where you do a thing called unit testing. Okay, so unit testing is things that are done by the programmer. Okay, so the programmer is writing a particular function that produces a report. Okay, so my job is to produce the code that generates a report by quarter. And so I'm the one writing the code, so I'm the one producing the unit tests that prove that work. So on each one of these tests, these types of testing, we're going to talk about two things: who does it, and what's the ultimate question that it answers. So in unit testing, it's done by the programmer, and it's basically to prove that one part works. In other words, if given this data, it produces the right output. Woohoo! Okay. Integration testing. Integration testing is done by the testing team and not by the developer. And what they basically do is see if all of the parts work together. So the unit testing is just doing this one part. Yep, this part worked, that part worked. Now we need to make sure the two parts work together. Okay, that's integration testing. So prove that the different parts work together, and it's done by the testing team. System testing. System testing is done towards the end of the process, not at the very end, but towards the end, done by the testing team, and it's to prove that the whole freaking thing works. So system testing says, let's go back to those performance specifications. Remember we talked about in the planning phase? Here's all the things it's going to have to do. All right, here's where we're going to go through the checklist. Did it do this? Does it meet this specification for timeliness and for this and for this and this? You go through and actually perform the test to say that it meets all the requirements. Doggone it, we're coming up on the 15-minute mark. So let's just stop here and pick this thing up again in just a few.